Okay, lecture 45. The ideal gas law. PV equals nRT. And R is 0.0821 liters atmospheres per kmol. This is new to have the gas constant in there. But unlike Boyle's law and Charles' law, we don't deal with two different states of the system, just one. So the gas constant gets left in there. And then because of that, the volume has to be in liters, pressure in atmospheres, temperature in Kelvin, and the amount has to be in moles. So we have to be a little more careful here. Let's take a look at the first problem. A sample of gas has a volume of 167 mils, so the volume is 0.167 liters. Have to convert over. A pressure of 88 millimeters of mercury, so 888 divided by 760 gives us 1.17. Now there's lectures on converting pressures and volume, so I assume that you know this, and that I'm going to move faster and faster when we get to these more complex problems. As far as the basic conversions, you should know those. If not, go back to the earlier lectures. This will be 300 Kelvin for the temperature. So I've taken the pressure, the volume, the pressure, and the temperature that were in the incorrect units and converted them. Now, how many moles of gas are present? Well, we rearrange the equation into this form, and then we put everything in. 1.17 atmospheres. The volume is 0.167 liters. And I'm just rechecking, make sure I got everything in here. This is liters atmospheres per kmol. It's troublesome to have to put in the units of measure, but you want those in there just to double check your work. If you're not paying attention and you just put in 1.17, 0.167, and 300, you could easily flip these if there's no units of measure on there. So now we can cancel them. And we see that we have a fraction, 1 over moles, in the denominator. So it's 1 over moles, which flips it back to moles. So we have the right units. That's what we need. About 300. We get 0.00793 moles of a gas. Ideal gas law says that all gases act the same way. That's an approximation there, but it's a really good approximation, so we don't have to state what the gas is. All the gases should act about the same, but if we want to know the grams of neon of a gas, and we're assuming neon in the grams of methane, we have to convert over. So this system is saying that we have a sample of gas, and so what mass of gas is present if it's neon? So we take now this is chapter 3 stuff, moles of neon, we're assuming that's what it is. 1 mole of neon is 20.2 grams of neon, going to the periodic table. And then for methane, this is actually one that we have used so much, or at least we've used carbon and hydrogen so much that you should know 1 mole of methane is 16 grams. If not, periodic table gives you all the information. And then we convert this is 0.160 grams of neon, and this is 0.127 grams of methane. So the moles are the same, but the masses of the same amount of gas, if we have two different samples at the same volume, temperature, and pressure, but they're different gases, the masses are going to be different. Okay. Now, number 2. This time we don't have the mass, we don't have the pressure, I think. Normally, the ideal gas law is used to find moles. That's what you most of the time use it for, is finding that N value. But here we have the N value. I just did it this way to show that you can find any of these values. You don't normally find the gas constant because we know it. It's something that's been memorized, but that's certainly a possibility that you could be given the pressure, volume, N and T, and solve for the gas constant. It just doesn't come up very much. So the pressure is going to be nRT over V. Number of moles is 5. That's given in the problem. R is 0.0821 liters atmospheres per kmol. The temperature is 333 Kelvin. They gave it to us in Kelvin, so that's nice. And the volume is 0.1 liter. Moles cancel. I do this all the time, even when I'm solving a problem on my own. You know, not for anyone's sake, just like when I'm correcting or proofreading an exam. I always put the units in there and cancel them just like that. You never want to get beyond that. Never want to feel like it's unnecessary. It'll save you a lot of headaches and heartaches, especially on exams, if you keep those units in and cancel them as you go. Okay, and oops. So that's number 2. We have the atmosphere, so we're all set there. Number 3. What is the density of nitrogen gas at 35 degrees Celsius and 0.915 atmospheres? Now the density, we know density, mass divided by volume, and usually the units are grams per mil. For a gas, because a gas has such a low density, normally we use units of grams per liter. If we use grams per mil, we end up with 0.001 gram per mil instead of 1 gram per liter. So these are the units that you normally use. You can certainly use these unless it's otherwise specified. I didn't specify it, but I'm going to use these because our volume of a gas from the ideal gas law is already in liters. Now we have grams. Grams isn't present in the ideal gas law, but we have N, which is moles. And as long as we know the gas, which we do, we can convert to mass, which is in grams. Okay, now you may have seen this, if you've done this type of problem before, you may have seen this done in a different way, where they take the equation and they convert this over to units of density, or they put density into the equation. I don't do that because I like to just stick with the equation that we have. And then, so I find moles, and then I know how many liters we have, and so we have moles per liter, and then I change to grams per liter based off of the gas that we have. So I like to always just stick with the equation that we were given rather than create a whole new equation. But that's up to you. If you've done it another way and you like that way, that's fine. The more complex problems there are, the more ways there are to solve it. I'm just going to solve it the way that I normally would. Okay, so N, we put in the pressure, put in the volume. Now the volume isn't given. Density does not depend on the volume of the gas. The density of a gas is the same if we have 1 mil or 1 liter or 1,000 liters or 10 million liters. The density is the same. So we get to pick the volume. You can put any volume in that you want. I put in 1 liter because it'll save us on the calculations, and well, that's mainly it. That's the reason I use it. But you can 0.0821 liters atmospheres per kmol. And this is where it kind of disturbs students that are getting to this level. You get a lot more freedom in some of the calls that you make on calculations. It seems like you're missing the information. It's not. You get to decide. I could have put in 2 liters in here, and you'd end up with the same answer. I'll show you how in a second here, so because that kind of goes against what you're used to as well. So this is 308 Kelvin. So we have liters cancel, atmospheres cancel, K cancel, we're left with moles. Goes on 0.915 divided by 0.0821 divided by 308. So we have 0.0362 moles of nitrogen. And that's going to be in 1 liter. Because I chose 1 liter. Now if I had chosen this as a 2, then this would be twice as much. So you can use any volume that you want. 1 liter just makes the calculation a little simpler. And the more ones that are part of a calculation like this, the more likely, the less work you have to do on the calculator. Now we have 0.0362 moles, and we can say per liter. That is definitely a concentration, but we want to convert to grams per liter. So we have 0.0, I'm just going to leave it as moles here for now. 1 mole of nitrogen is 28 grams. and I come up with 1.01 grams of nitrogen. And to finish the density, we know is 1.01 grams of nitrogen in 1 liter. That's what we chose it to be, so our density is now, you can say, well, you don't really have to divide by 1, but in a way you do, because this is a different unit of measure here, and now we divide by our volume. So just to finish up, if we had used 2 liters here, then this value would have been twice as much. So this value would have come up to be 2.02. 2.02 divided by 2 liters give us the same density. Has to. So whatever volume you want to use, you can use. You want to use 555 liters? Absolutely. It just means you're going to have a little extra work to do on your calculator. Okay. And then, the last one, it says, what is the density of uranium hexafluoride? So let's say instead of nitrogen, it turns out that we had uranium hexafluoride in our sample. Somehow that unbelievably deadly gas got into our general chem lab. That's no problem. It is a problem in the lab. And this is actually 352 grams uranium hexafluoride. Just know that one off the top of my head. Use it a lot. So this is 12.7 grams uranium hexafluoride per liter. And even though I know it off the top of my head, I'm going to multiply. Just check on. Yeah. So you can see that if it's nitrogen, 1 liter of nitrogen, it weighs 1 gram, about the mass of a medium-sized paperclip. But if you have uranium hexafluoride, it's 12.7 grams. You'd actually be able to feel that mass on your hand as it's pressing down, because it's such a large molecule. Even though it's the same number of moles, it weighs more per liter. Okay. 4. This one is a little tricky. There's a lot to it. An unknown liquid weighing. Unknown liquid. And it's unknown how much it weighs at this point. I forgot to get rid of that. An unknown liquid is vaporized, so forget about that. Is vaporized inside an open 150 ml container at 100 degrees Celsius and a pressure of 745 millimeters mercury. The container is capped and the vapor cooled back into a liquid. This remaining liquid is found to weigh 0.556 grams. What is the molecular mass of the liquid? Okay, the reason that we don't work with the mass of the unknown liquid to start, you can have a beaker. Let's say it's just a bottle like this. And you have it half filled with this unknown, and you heat it up, and it vaporizes. Well, even though, let's say it's 50 grams of this stuff, well, it vaporizes, it turns into a gas, most of it makes its way out. What you're hoping for is once it's vaporized completely, whatever was in here, all of the air has been pushed out. All that remains inside this volume is the vapor of the unknown liquid. Well, since it's a vapor, it's now a gas, and it follows the ideal gas law. So if we know the volume of this container, we know the temperature of the vapor, and we know the pressure, we can find the number of moles. If we know the number of moles, and we divide that into our mass in grams, we end up with grams per mole, and that's the molecular mass. Very, very clever. So what we do is we take the unknown liquid, heat it up, boil it off, and actually it doesn't matter if there's any air in here or not. The vapor is going to take up the same volume, but usually most of the air is pushed out. Once the liquid has become a gas, it obeys this law, the ideal gas law. We can then find the number of moles. Now, once we cap it off, and then the gas that has that volume is trapped inside, we cool it down, it becomes a liquid. The reason we do that is so now we can weigh it. So the ideal gas law, when it's in the vapor form, will give us N. Once we cool it back down, the liquid, we can weigh it, that gives us M. M divided by N gives us the molar mass. Very, very clever. Okay, and what this allows us to do is take an unknown liquid in the lab and determine its molecular mass, which allows us to find its in AMU, so it allows us to learn a property of one particular molecule. So a microscopic property that can be determined by just heating something up in the lab. All right, so how we do this, we have to find N. So we have PV RT. So 745 divided by 760 this is 0.980 atmospheres. The volume is 0.15 liters. 0.0821 liters atmospheres. I know that you're as tired of writing this as I am, or even just watching me write it, but you have to put those in. It really, really do. 373. You have to put the units in. Cancel. Make sure that you have what you're after. Of course, you might not notice it as much because I sit here and I do out several of these lectures at once, so I'm sitting in this room for hours at a time doing the same thing over and over, the same kinds of calculations over and over. Okay, so this is the number of moles. Now they say that the mass of the liquid was found to be, the gas, or the liquid that was a gas. We now know how much the liquid weighs, so we know how much the gas weighed. We divide by this number. And normally it's in the tens or hundreds as far of grams per mole. This one is 116 grams per mole, which means that one molecule weighs 116 AMU. So we can take a macroscopic system and very simply find the mass of one molecule. Pretty slick. Okay. Then one more variation here. I gotta move pretty quickly on this. So using the information from problem 3, determine the molar mass of uranium hexafluoride. So we have the temperature is, this is from 3, you can always double back, I'm just going to write everything out here. The pressure is 0.915 atmospheres, and if I run out of time then I'll just tack it on at the end here onto another video. And the volume would take to be 1 liter. Now, we want to find the molar mass. So the molar mass, capital M, lowercase m, is going to be m over n grams per mole. Now we determined in the problem that we have from 3, we have this number of moles, and the okay, well, I'm running out of time here. We'll just stop. I hate to tack on one last problem, but that's fine. Everything else worked out really well, so we're going to stop there.